and welcome to a new episode of DiagnoseDan. Today we're working on this 09 Audi Q5 with a 3-liter V6 TDI diesel engine. And the customer complaint is the check engine light is on. So let's diagnose this together. Now first of all, let's hook up the scan tool and see what codes we have. Now, I've got a throttle actuator, bank 1, range performance fault, and I've got 2 Egr circuit faults. In this video, I'd like to concentrate on the throttle actuator control, bank 1, range performance fault. Now when you rev a diesel engine, you don't rev it by opening the throttle plate. You rev it by injecting more fuel. So you might wonder, why does a diesel engine need a throttle body in the first place? And that's actually a very good question. There are 3 main reasons why a throttle body is used on a diesel engine. When you shut down a diesel engine, you do it by cutting the fuel. Now a diesel engine has got a higher compression ratio than a petrol engine. And because of the high compression, when you shut it down, it tends to shake when you stop the engine. Now by installing a throttle body, it allows you not only to cut the fuel, but also cut the air supply, resulting in a lower compression and a smoother shutdown. Now in this particular model, the Egr gases get sucked into the engine over here. Now typically, inside the intake manifold of a diesel engine, there's no vacuum, making it very hard for the Egr gases to get sucked into the intake manifold. Now by installing a throttle body, we can temporarily restrict the airflow into the engine, creating a pressure drop for better Egr performance. The third reason we need a throttle body on a diesel engine is to regenerate the NOx cat. To regenerate a NOx cat, we need a slightly rich mixture. We achieve it by using a throttle body to temporarily restrict the airflow into the engine, creating a rich mixture. Now that we finally know what the throttle body on this diesel engine is for, can we finally diagnose the thing? Now the throttle body lives in between the intake manifold and this turbo hose over here. It is held down by 3 screws and a hose clamp. So I got it out of there, but I left the connector attached to the throttle body. So electronically, it should still work. I'm going to use the scan tool to bidirectionally control the throttle body and command it to close. And now that it's out of there, it should be easy to see if there's any response. I'm going to command the throttle body to close, so let's see what happens. And when I hit the start button, it should. So let's see what happens. And as you guys can see, there's absolutely no response from the throttle body. Now that we know our throttle body is non-responsive, the next thing we should do is take a look at the wiring. So let's take a look at a wiring diagram and do some measurements. So I've looked up the wiring diagram for the specific engine. Let's find throttle body. And it is actually over here. It is M24, and we can see that on pin 1 there's a ground. On pin 2 there's a power coming from this 15 amp fuse over here, and there are 2 communication wires running in between the throttle body and the PCM. Let's start out by checking the power and the ground wire coming to the throttle body. So let's back probe the ground wire on pin 1 and the power feed on pin 2. And if the power and the ground are okay, my test light should light up. Now, when I took a look at the wiring diagram of this throttle body, the little transistor symbol drawn into the throttle body indicated to me this throttle body isn't just a motor and a potentiometer, it's actually a bit smarter than that. The other 2 wires, besides the power and the ground, are actually communication wires. One wire is coming from the PCM to the throttle body, and it's commanding it to open and close. The other wire is a feedback signal to report back to the PCM if it actually did. I've got pins 3 and 4 back probed at the throttle body. So let's start the measurement. And let's zoom in a little bit. Now let's use the scan tool to command the throttle body to close again. And we can actually see the command changing from opening to closing. Now if we zoom out from our recorded waveform, we can actually see what the other channel has been doing. And the other channel created this waveform, telling the PCM it didn't open or close. Now that signal we saw coming from the PCM commanding the throttle body to close was actually a PWM signal. Now, to get a better understanding of this signal, let's learn a little bit more about PWM, or pulse width modulation. To get a better understanding of PWM, I'm using this blower motor and this jump starter as a power source. I've got the negative side of the motor connected to the negative terminal of my power source. Now we all know that when I connect the positive side of the motor to the positive terminal of the power source, the blower motor is going to run at full RPM. If I want to slow the blower motor down, I can achieve this by briefly touching or pulsing the power source. Now, as I was turning the blower motor on and off, you could see the RPM of the motor wasn't very steady. Now that's because I'm not precise or fast enough. So in the next test, we're going to use this tool, which I got from Ryan Automotive, and I will leave a link in the description of this video. It is a great tool for diagnosing systems that use pulse width modulation. In this test, I've got the blower motor hooked up to the tool and the tool hooked up to the power source. Now let's do the same thing as we did before, but let the tool do the pulsing for me. Now this tool used the PMW signal to increase and decrease the speed of the blower motor. But to exactly understand how it's doing this, we've got to learn more about the basics of pulse width modulation. A PWM signal uses a fixed frequency. Frequency is expressed in hertz, and hertz is the number of times something occurs within 1 second. Now, it isn't the frequency or the number of times we turn the motor on and off that's causing the increase or decrease of the speed, but it's the actual on time. Now, to get a better understanding, we need to look at a waveform of our PWM signal. Now, since PWM signals aren't only made to drive blower motors, in the next test we're going to use an Egr valve. With the tool, we can test this Egr valve by opening and closing it. I'm driving the Egr right now. And let's count the number of pulses on the screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now the screen time is 100 milliseconds. This means there are 10 of these frames within 1 second. So 13 multiplied by 10 means a frequency of 130 Hertz. Now you can easily check the frequency using a multimeter. Just put it on a Hertz reading, and the reading right now is 130 Hertz. This means this valve is being turned on and off 130 times each second. Now let's open this Egr valve, and in the meantime take a look at our waveform. Now the frequency should remain the same at all times, so the same number of pulses across the screen at all times. Now although this valve is being turned on and off 130 times each second, you can see there is still time in between those pulses. Now the time this valve is being switched to a power source is called the on time. And right now, this is close to 0%. Now the time this valve is not being switched to a power source, or the valve is off, is called the off time. And right now, this is close to 100%. Now let's open the Egr valve and look at our waveform. As you saw in the example, the frequency of our signal remained the same. The only thing that changed was the on and off time of our component. Now this is what we call a duty cycle. And a duty cycle is expressed in a percentage of on time. Now in the next clip, I want to show you 3 examples of duty cycles. The first being close to 0%. The second being close to 50%. And the third duty cycle being almost 100%. At a 0% duty cycle, the component is never being switched to a power source, so it won't work. Now at a duty cycle of 50%, the component is being switched to a power source half of the time, so it will work at half its potential. Now at a duty cycle of 100%, the component is constantly being switched to a power source and it will work at its full potential. Now if you haven't got a scope, but if you want to check the duty cycle of this Egr valve to see if it's being commanded on or open, you can still use a multimeter which can read duty cycle. Now on this tool there's a dial that goes from 0 to 100%. Now let's dial up the duty cycle and watch the reading on our multimeter. Now we already saw that duty cycle is a great way to control an Egr valve or a blower motor. But there are countless other applications in the automotive industry. I want to show you 2 more. Let's control throttle body using duty cycle. And remember the old days, we had separate lightning bulbs for separate functions. For instance, lightning and a brake light. Now using duty cycle, we can combine these functions in one single light bulb by altering its brightness. So one moment it's your lightning and the next moment it's a brake light. We have got to talk about one more application of PWM signals, and it might be the most important application for diagnosing our Audi. PWM signals can be used as a form of communication. Now let's use our Audi as an example. The PCM is not directly controlling the throttle body motor. That's up to the electronics inside the throttle body itself. But the PCM is telling the throttle body by duty cycle what percentage of throttle valve opening is desired. So in this example, the PWM signal or duty cycle is not controlling the throttle body, but it's used as a form of communication. Now we verified the power and we verified the ground, and we actually saw the PCM commanding the throttle body to open and close. So I decided to take a closer look to this throttle body, and this is what I found. Actually, a hole burned into the electronics inside the throttle body. Now, since our old throttle body was fried, I ordered a new one. So let's install it and let's command it to close again and see if it works. I'm curious. I'm really curious. I'm curious. Another one diagnosed and fixed, and we got to learn a little bit more about PWM signals. Interesting, right? Now, if you like this video and if you want to learn more, please subscribe to my channel. And when you hit the bell, you will get a notification each time I post a new video. DiagnoseDan, fixed it again. See you next time, guys.